My name is Tiantu Xu, a third-year PhD student at Purdue ECE. Today my topic is VStore, a data store for analytics on large videos. First, why do we need video analytics? Because the video data is explosive. The annual shipment of surveillance camera grew by 10x in the past decade, up to 130 million shipments per year. So to create robust smart city solutions, we need to transform the enormous video data into valuable insights. And then what is video analytics? It's like a user files a query like when did a man with a blue shirt show up yesterday? And through running multiple computer vision algorithms on the video data, we extract the information like man with a blue shirt show up between 11:05 p.m. to 11:07 p.m. last night. So let's take a deeper look into how does a query look like. The query is usually composed by a cascade of multiple vision operators. This is a pipeline from prior work no scope. It has 3 stages. The frame difference detector can run at very high speed, 100k frame per second, to detect the nearby 2 frames, whether those 2 frames have difference. And the specialized neural network can run at 27k fps. However, the function is also limited due to its limited number of convolutional layers, and it can only do one job, to detect whether this is a car or not. And if it is not confident, the frame will go to a full neural network to make the final decision. So we can see that the operator speed varies in a very large range from 10 to 100k fps. And at the query time, the user can also select the operator accuracy, which highly depends on the video formats. So it looks pretty simple that video analytics is like we feed every frame of the video to the cascade operators, and those operators we choose from operator library, and we can directly get the result. However, for analytics on archival videos, this is not always the case. Because in this case, we need to ingest the video from the surveillance camera and store those videos on the disks. And whenever a user wants to have a query, we retrieve the video data, and finally, the final step is the consumption. So archival video analytics is a crucial complement to live video analytics, which is a major focus for many prior work. Live video analytics means that we run vision operators in real time when the video frames keep flowing in. However, archival video analytics has few benefits. The first is the lazy ingestion, because it only needs to do minimal job at ingestion time, and only a small fraction of videos will eventually be queried. So compared to the live analytics, it saves the GPU time. The second benefit is query specification. The users know their query better, and they can also choose an accuracy level at query time. The third is exploratory analytics. The users may interactively revise their queries because the goal is not always clear at the beginning. So to this end, we advocate for a new video store that orchestrates the ingestion, storage, retrieval, and consumption. And we have 3 requirements. The first is to satisfy the operator accuracy, which means the video we store and retrieve must meet the accuracy level specified by the user at the query time. The second is retrieval never bottlenecks the operator. When we retrieve an encoded video chunk from the disk, we must ensure that the decoding speed is faster than the operator consuming speed. And the third is high resource efficiency, because for each state we have different resource limits. The first class design concern here is to control the video formats, and there are 2 places to tune those formats. The first is at the ingestion time, it's for storage purposes, and the second is at the retrieval time for the consumption purpose. So the fidelity knob includes the resolution, frame rate, the crop factor, and video quality. And the coding knob consists of the speed step and the keyframe interval. So knob impacts are very complex. The radar chart is the result of tuning the fidelity knob at the retrieval time. So A, B, and C are 3 different formats, very different on each dimension. However, running the specialized neural network on those 3 formats has nearly the same result. However, they have a different trade-offs on each of the stage. So for example, if we take a look at the format A, it has a bad quality, so its storage is very cheap. However, when we look at format B, it has the best quality, so the storage is very expensive. However, they can reduce the video, they can remove some video data because they don't need to compensate their bad video quality like format A. So the consumption speed of B is very fast. The same thing also applies to format C. Both of them, all of them has different trade-offs on each dimension of the fidelity knob, and each of them have a very large difference on the resource cost. So if we take the format A as a baseline, when we change to format B, the storage will go up by 8x, and the retrieval cost go down by 2x, and the consumption speed goes up by 10x. And for format C, the storage cost is 2x of format A, and the consumption cost is 2x lower than the format A. So the coding knob impacts are also very complex. When you encode the videos, you can choose whether encode the videos slow or fast. From the slowest to the fastest, the storage size will go up because when you encode fast, the encode efficiency is not very good. However, when you retrieve those videos, which means that when you decode those videos, you have a lower cost. The keyframe interval is also the case. So when we encode the videos, it's encoded in a chunk, and each chunk has multiple frames, like from 5 to 250. And if you encode 250 frames in one chunk, the storage will be very low. The storage size will be very low because it has higher encoding efficiency. However, when you decode those videos, you need to decode the whole chunk, so the retrieval speed is very slow. So at ingestion time, we tune the knob for storage purpose, and at the retrieval time, we tune the knob for consumption purpose. So the video formats we store at the storage is called the storage format, and the video format that we consume for vision operators is called consumption format. And there's an M to N mapping from the storage formats to the consumption formats, which I will talk about that in detail later. And the knob also has two constraints. The first is the knobs that we tune at the ingestion time must be at least richer than the knobs that we tune at retrieval time. And the retrieval speed must be faster than the operator consuming speed. So to design such a video store, we're challenged by the complex knob impacts, the optimization of multiple resource types, and the expensive profiling. So our key idea is the backward derivation of configuration. We derive the optimal set of video formats in the opposite direction where the data flows. So let's take a deeper look into detail. So when there's a query, we retrieve the video data from the storage and convert it to the consumption format that meets the need of each video consumer at each accuracy level. So the backward derivation of configuration is divided into 3 steps. The first step is to configuring the consumption format. VStore will optimize the profiling in a high-dimensional fidelity space to get the cheapest format given the target accuracy of a specific operator. The second step is configuring storage formats. VStore iteratively coalesce the consumption format to storage format to respect the ingestion budget, which means that if the system can afford ingesting the M formats. The third step is the erosion plan. So VStore trades the consumption speed to save the storage space for aged video segments. So due to time limit, I will only talk about the second technique, which is configuring storage formats. So our goal here is to we have N consumption formats, and the number is very huge, and we cannot afford storing so much consumption format and ingesting so much consumption format in real time. So we need to pick the consumption formats to coalesce two of them into one. And after multiple rounds, we expect to see that the ingestion cost will go down because we have dramatically reduces the number of the consumption formats because we coalesce multiple of them into one storage format. However, the enumeration is unaffordable. For example, if we have two consumption formats, there are two ways to deal with this. The first is to coalesce, the second is not to coalesce. However, when the number of consumption formats grow up to 12, we have more than 4 million of possible storage format sets, which is unaffordable. However, this question may sounds like a very simple hierarchical clustering problem. Basically, you can think about a solution like you normalize the normal values of the consumption format on each dimension from into 0 and 1. And we always try to pick the consumption format that has the closest Euclidean distance to coalesce until we get the satisfiable ingestion cost. However, we have done some experiments on that. Because knob impacts are too complex, simply normalize all the values on each dimension will fail to give the optimal set of video formats compared to our solution. And it also incurs 2.2x storage cost than our approach. So our approach works like this. So the first step is to harvest the free coalescing opportunities, which means that both the ingestion cost and the storage cost will go down. For example, in the two formats I have tagged red, the first format is the superset of the second format. So we directly coalesce those two formats into the formats on the top. And because we reduced the two formats into one, so the ingestion cost will go down because transcoding to one format is much cheaper than transcoding to two formats. And also we have reduced the storage cost because we avoid storing the video formats on the bottom. And here we will check whether ingesting those video formats is below the ingestion budget. If it is yes, then we are done. But if it's no, then we need to further coalesce the consumption formats pairs into storage formats. For example, the 360p 5 fps and 180p 15 fps. None of them is a superset of another. However, to respect the ingestion budget, we need to sacrifice the storage here. So we get the max number on each dimension to be the fidelity value of the storage formats, and in this case, the storage cost will go up. So we implemented VStore like this. So for ingestion and retrieval, the major job is transcoding. So we implemented on FMPEG using the libx264 and the NVINC, and we use LMDB as our storage backup, and we ported two video analytics engines, NoScope and ALPR, as our as a provider for our operator, and we run experiments on 6 outdoor surveillance videos. All of them are a few hour videos. So this is the sample configuration of video formats. We have 6 operators and 4 accuracy levels. So in total, we have 24 consumption format. So after our coalescing approach, we shrinks to only 4 storage formats, which saves a lot of storage space and ingestion cost. So if we look deeper, in the first column, the difference detector, it can run up to 30K frame per second. However, the video format is also very cheap here, and decoding those video formats is slower than consuming those video formats, which is 30K. So in this case, we need to store the raw video formats. But fortunately, because the video fidelity is very, very cheap, so it won't incur too much storage cost. So if we compare to neural network, it runs very, very slow. So and it needs very high resolution to get the satisfiable accuracy that is defined by the user. So this is our major result. We have two baselines. The first baseline is 1-to-1, which means that we store the highest fidelity and consume the highest fidelity, which is 720p at 30 fps in our case. So this baseline is bottlenecked by the video retrieval and consumption. The second baseline is 1-to-n, which means that we store the highest fidelity, and we, at query time, we retrieve the consumption formats on the fly to satisfy the operator's need. However, this baseline is bottlenecked by the retrieval. So the green line is our system, and it outperforms the baseline by 15x because it is never bottlenecked by retrieval. And when accuracy goes down, the query tolerates cheaper video formats, and the retrieval is also proportionally cheaper. So this is the result, the final result of all 6 videos. And we can see that at each accuracy level, on each video, our system outperforms all of the 2 baselines. So to sum up, we build a data store for fast, resource-efficient analytics over large archival videos, and our key idea is the backward derivation of video formats. And we ensure that retrieval never bottlenecks the vision operators, and we also respect to multiple resource budget. And our work urges the research on storage, which is the dark side of computer vision research. Thank you.